Hello, my name is Gary Millette, and today I'm going to talk about topic number 6 for ELE-110 Electronics for Technicians 1. This is a presentation about series resistive circuits, parallel resistive circuits, and combination resistor circuits, which are actually combinations of series and parallel circuits. So I call this topic number 6, but in reality it turns out this will be posted probably 3 times for 3 weeks in a row on the Blackboard website for the course. So let's get started. First off, resistors in series. These diagrams, A, B, and C here, show the top one, 2 resistors, R1 and R2, and they're between terminals A and B, and they are in series. And then in part B, we have between terminals A, B, and C, excuse me, A and B, there's no C there, resistor R1, R2, and R3, and they're in series. And finally, part C, there's terminals A and B, and there are 4 resistors in series wired between terminal A and B, R1, R2, R3, and R4. So again, what happens is series resistors are wired end to end. And in each case, the real important thing is here, the same current flows through each resistor. The electrons that form the current cannot leave the circuit. They can't fly off the wires or disappear anywhere. So in the very bottom of the slide, I say in a series circuit, there's only one path for the current to flow. The same current flows through each component in a series circuit. You might consider a series circuit like a piece of pipe. Whatever flows in a piece of pipe, water will say on one end, has to come out the other end. So those are series resistors. Now, the current in the series circuit depends on what the total resistance is. So here we show a graphical or pictorial picture of 3 resistors and a battery. And in this case, we're showing again conventional current, the current leaving the positive terminal going around to the negative terminal. We know the electrons go the opposite direction from the negative terminal to the positive. And to the right, we have a schematic, and it shows a battery with a polarity, in this case, kind of maybe just to be general, the battery is minus to plus, with a minus being on top. And what happens is we have the schematic labeled as point A, B, C, and D. Those are called nodes, by the way. There's resistor R1, R2, and R3, and it shows a conventional current again, flowing from the positive side all the way back to the negative side of the battery. Again, for a complete circuit, there's no place the electrons can go other than through the components of the circuit. And for the figure 5.7, it says current into any point in a series circuit is the same as the current out of that point. So again, current is the same in all components in a series circuit. In this pictorial diagram, we see a battery, the 3 resistors we had previously, and we have 4 current meters. And the 4 current meters, you notice, have all the same 1 amp through them. And again, the current meter has to be what? It has to be put into the circuit. The schematic on the right-hand side is the same as one on the prior slide, except now we see the current meters. By the way, an aspect of this you might want to pick up on is if you want to know how to put the current meter, what polarity to put it in, what you do is you put the minus lead of the current meter closest to the minus lead of the battery, and the plus lead of the current meter closest to the plus lead of the battery. And that will give you a correct potential for the meter. So the concept of total series resistance is quite important in a series circuit. Let's take a look at figure 5.11 here. The total resistance increases with each additional series resistor. So it's fairly intuitively obvious that the total resistance of a series circuit is the sum of all the resistors in the circuit. By the way, when Ohm years ago did his experiments, what he did was he took and he had pieces of wire. So he would note the amount of current that flowed with a certain battery for, say, 10 feet of wire, and then he would take and increase that 10 feet to 20 feet of wire and discover the current would go down by a factor of 2, or be 1/2. That's because 20 feet of wire was 2 times more resistance than just 10 feet of wire. In these diagrams, A, B, and C here, we show the first one on the far left has a 10 ohm resistor. Then in the middle one, we have 2 10 ohm resistors, and we indicate the total resistance there would be 20 ohms. And the one on the far right, we have 3 10 ohm resistors, indicate the total resistance to be 30 ohms. So series resistor values add. The total resistance in a series circuit is equal to the sum of the resistors, of the individual resistors. So here's the formula, and we have an example here. We've got a voltage source called V sub S, and a 56, 100, 27, 10, and 47 ohm resistor. And the equation up above says R total is R1 plus R2 plus R3 plus ... plus R sub n. That's a general formula. If you only have 3 resistors, you just have R1 plus R2 plus R3. If you have 5 resistors, the subscript of the last R will be R5. So down below, we have our total is 56 plus 100 plus 27 plus 10 plus 47 for the 5 resistors shown in that circuit, which totals up to 240 ohms. So again, this example to the left shows how one deals with the series circuit. One simply adds all the resistor values that comprise the series circuit to calculate the total resistance. So here's another example. This is example 5.4, and it asks what is the total resistance R sub T in the circuit of figure 5.15. So there's a battery there, V sub S, a 39, a 100, a 47, a 100, a 180, and 68 ohm resistor. And down below they do the mathematics to get that totals up to 534 ohms. Again, you may be familiar with this material. If you are, you might want to skip over the examples. What about the total resistance of equal value resistors? Well, the equation here says R sub T, or R total, is equal to N times R, where N is the number of resistors. So as example 5.4.6 down below, find the resistance total of 8 22 ohm resistors in series. We could simply add all those 8, or it might be a little bit simpler to multiply 8 times 22 and got 176 ohms, as shown here in the example. So here's another Ohm's law in a series circuit. So if I have a circuit like this, shown here in figure 5.17 of example 5.7, shows a 25 volt voltage source. It's got an 82, a 22, a 15, and a 10 ohm resistor. So the question is, find the current in the circuit. Well, what you have to do first is you have to make an equivalent resistance of all those series resistors. So first determine R total, then use Ohm's law. In the example solution here, they show they've added the 4 resistors together. They get 129 ohms. Then they take and say I equals V sub S over R total, which is 25 volts over 129 ohms, which is equal to 0.194 amps or 194 milliamps if you take and move the decimal point over 3 places to the right. So to use Ohm's law in a series circuit, one needs to calculate the total equivalent resistance for the series circuit. Once the total resistance is known, then Ohm's law may be used to find the circuit current. We digress a little bit by taking a look at voltage sources in series here. So in figure 523A, I show 3 1.5 volt batteries. Now you may be familiar, 1.5 volts batteries are the nominal voltage for what we call D cells. Those are bigger batteries, or double A's or triple A's. And it turns out that if I put 3 of them in series with minus to plus, minus to plus, minus to plus, I'll get a total of 4.5 volts. On the other hand, in figure part B of figure 523, notice that the middle battery, the polarity is plus to minus, with a plus on the left-hand side as opposed to the 2 outer batteries with a plus on the right-hand side. What happens is that voltage subtracts, and basically you could say 2 of those batteries just cancel out, leaving 1 battery, or the 1.5 volts. This is why if you have any battery-operated electronic equipment, you want to be very careful putting the batteries in the correct polarity, which is usually shown, either by the fact the spring goes to the base of, say, a double or triple A, and the positive or top of the battery goes to some type of other connector. So voltage sources in series add algebraically. And again, most would say this is intuitively obvious, that the total voltage produced by a series battery arrangement is equal to the algebraic sum of the individual battery voltages. So here's a kind of interesting diagram. It shows how we might arrange various batteries to give us different things. On the top left, we see 50 amp hours, and that's the rating of a battery, how long it can produce the current for. And it says 50 amp hours at 48 volts. So if I put 4 batteries in series, 4 12-volt batteries, what happens, I increase the voltage, and my 50 amp hour rating is the same as any individual battery. In the middle, I put 4 batteries in parallel. Well, we haven't talked about parallel circuits yet, but this is a parallel circuit. And what happens here, excuse me, is the battery voltage stays the same at 12 volts, but the number of ampere hours, 200 amp hours, increases 4 times what it was before. So the diagram on the top left, I get 4 times the voltage. The diagram in the middle, I get 4 times the amperage. And then finally, over on the far right, if I want to get more amp hours and higher voltage, I might do this arrangement where what I do is put 4 12-volt batteries in series to get 48 volts. Then I have 2 sets of these 4 batteries in series to get a total of 100 amp hours. So again, hopefully that's fairly intuitively obvious. So here's a Prius battery unit. The battery unit for a Prius is made up of numerous cells that eventually yield several hundreds of volts. Note that the wires are coded orange to indicate a dangerous high voltage. Most standard wiring in a car is red and black, red for the positive, black for the negative or ground. Now we go to orange color coding for high voltage. And these are all modules. If you had a Prius battery, it would appear that I could take and replace a module if it goes bad. This brings us to Kirchhoff's voltage law. And Kirchhoff's voltage law states that the sum of all voltage drops around a single closed loop in a circuit is equal to the total source voltage in that loop. The algebraic sum of all voltages, both source and drop, around a closed path is 0. So that could be written as the voltage source is equal to V1 plus V2 plus V3 plus ... plus V sub n, where n is the number of voltage drops. If I had 3 resistors, this equation would reduce to the source voltage would be equal to the voltage drop across V1 plus V2 plus V3. So here's a graphic example. And again, we have 3 resistors shown there. And you notice that there is a voltage drop V1, V2, and V3. And if I take and subtract them from the source voltage, I'll get 0. So a way to look at this is pretend you could stand on the negative terminal of the battery and could start walking around counterclockwise. So you go towards terminal B, you walk up through resistor V3, which raises a voltage plus V3. You go through resistor V2, now going left up through the top wire, and now you've gone up through an additional V2. Then you go actually down through V1, but that goes up in voltage. So you've added V1 plus V2 plus V3. Now you go back to the battery and you would go through a fall of V sub S, which is applied, and you get back to the negative terminal, and now you have a total voltage drop of 0. So again, Kirchhoff's voltage law is the sum of the voltage drops equal the source voltage. And basically it's nothing more than a statement of the conservation of energy for a circuit. You can only have voltage drops in a circuit that add up to the voltage applied. So here's another little graphic that shows a battery, some V sub S, and it turns out that V sub S is 10 volts because that's what the meter on the right tells us. Then we have 2 resistors of unequal value, so I get 5.5 volts across one and 4.5 across the other, which adds up to the 10 volt of the source. Now, by the way, an interesting fact here is in this series circuit, what have I done? I created 2 different voltages than what the battery voltage is. You discover for efficiency, we usually have equipment that plugs into the wall, and we have a power supply that converts the AC to DC in that piece of equipment to run the electronics in it. But if we need other voltages, we can provide those other voltages by using series circuits to provide voltage drops to alter what the power supply voltage was in the first place. Here's another example. This one says determine the source voltage in figure 534 where the two voltage drops are given. There's no voltage drop across the fuse. And the fuse is what? That's a safety protection device. So it shows R1 with a plus 5 volt drop across it, and R2 with a 10 volt drop across it. So those add up to 15 volts. That would be the value of the source voltage V sub S. And the solution is shown down below. Something called voltage dividers is something we should take a look at. So here's a 2 resistor voltage divider, and I just mentioned the idea that you can create new voltages. A series circuit acts like a voltage divider. The source voltage divides up among the series resistors in accordance with their value of resistance. So here's an example of that. This figure 539 shows a 10 volt source, and I've got a 100 ohm and a 56 ohm resistor, it looks like, which is a grand total. They figure out R sub T is 156 ohms. They now do a calculation where V1, the voltage across resistor 1, is going to be R1 over R total times V sub S. So 100 divided by 156 is equal to 6.41 volts. That'll be across R1. Then what's the voltage? Well, we could just simply subtract that from 10 and get 3.59 volts across R2. Or we could use a voltage divider formula again, R2 over R total times V sub S, which is 3.59 volts. The other way to do this would be to take and get the total resistance, which they've done, of 156 ohms, and then divide that into the 10 volts to determine the current, and then multiply the current, which is the same in both resistors, since it's a series circuit, times the individual resistor values to get the voltage drop across each resistor. Here's another example, practical, of a gas tank, and you might be surprised that indeed this is very often how gas tanks work in cars. There's a storage tank on the part A there, figure 545. Part A of that figure shows a float and a level sensor, a processing circuit, and then a volume display. Well, most of the cars today will have a meter or something that shows how much gas is left, or they might have a digital readout that says, oh, you got this many more miles before you are on empty. So a little more detail, this level sensor is shown on part B, where it shows what's called a potentiometer, resistive element potentiometer, and where the float is gives rise to where the moving contact touches that potentiometer. So if the float is low, that moving wiper contact will go back up towards the top, which would show an empty tank, or if the tank is full, the float would rise higher and the wiper would go down towards the bottom of the potentiometer and say that the tank is full. So again, the schematic for that is on the figure C. On the right-hand side, the output voltage is a measure of how much gas is in that tank. What about the power in a series circuit? We've talked about power in another presentation. The total power in a series circuit is the sum of the individual powers in each of the series resistors. So power total is P1 plus P2 plus P3 plus ... plus P sub n, where again, n is the number of components in the circuit. So if I had 2 series resistors, I'd have power total is equal to P1 plus P2. How would I find that power? By again multiplying I times V, or taking V squared over R, or multiply I squared times R. Again, the 3 power equations. How about measuring voltage across a resistor? Well, to measure the voltage across a resistor, one places the voltmeter across the resistor. This shows a voltmeter V across resistor R2. And again, to get the correct polarity for a voltmeter, you put the plus lead of the voltmeter closest to the plus lead of the power supply, or in this case, the V sub S source. The negative side of the voltmeter goes closest to ground. And here's a couple examples of measuring voltage across R2. In this one on the left, figure 557, part A, it shows I put the voltmeter between point A and I go to ground, and I measure a certain voltage. Then in the diagram to the right of it, I put the voltmeter at point B, or node B, and notice that the number of red lines have gone down the voltmeter, so the voltage potential is less there to ground. And then to figure out the voltage across R2, see the equation VR2 is equal to VA minus VB. So let's just say at point A we measured 10, and at point B we measured 5. So the difference between 10 and 5 is 5 volts And again, the polarity across R2 would be the left-hand side is closest to the plus input of the battery or source. Therefore, the left side of R2 is plus, and the right side is negative. So I'm going to just pause for a second here. Let's summarize the fact that resistors in series all have the same current flowing through them. They are the only path for the current. And that brings us to resistors in parallel. Now, again, this is topic number 7, but I'm going to leave this as topic number 6 for the label for this presentation. So let's start again on resistors in parallel. In a circuit, each path for current flow is called a branch. So we see figure 6.1 there of resistors in parallel. So a parallel circuit consists of more than one current branch. So you see in part A that the source voltage has resistor R1 and R2, and both of those resistors are right across that source. Then in part B, we see again with conventional current flow, a total current leaves the voltage source, V sub S, towards point or node A. Some of that current breaks down and goes through resistor R1 downward. Some continues on to resistor R2, and then at node B, those two currents combine to form I sub total. We would call the first current I R sub 1 and the second current I R sub 2 if we were going to put, mark them or label them in a certain way. So the big thing about parallel circuits are the same voltages across each branch of a parallel circuit. So here we have a voltage source V sub S, and we have resistors R1, R2, R3, and R4, and they're all basically across the same power supply V sub S. And there's a total current that comes out of the battery or source, and a total current that comes back to it. In this case, they're showing conventional current, again, going from plus to minus. We know the electrons go the opposite way. And you see a current through R1, through R2, through R3, and through R4. Okay, so in the circuit shown here, there are 4 branches. All the blue nodes are the same point electrically, and all the green nodes are equivalent also. Each resistor has the same voltage across it, the applied voltage V sub S. One can determine the current through each resistor by using Ohm's law. That is, we take I1, for instance, would be equal to Vs divided by R1. I2 would be Vs divided by R2. I3 would be Vs divided by R3. And finally, I4 would be Vs divided by R4. And we would add them all up to get I total. So here's a graphical picture here. As mentioned before, in a parallel circuit, each component has the same voltage across it, but not necessarily the same current through it. So here we see on part A, a battery, and it's listing all the nodes A, B, C, D on the left, E, F, G, and H on the right. And they're wired, it's a very conventional way of wiring them to show they're in parallel, all connected to what you might call a bus or rail on the left and right-hand side. On the right-hand diagram, part B, it turns out we show the same 3 resistors, but they're individually wired to the battery terminals. Exactly same circuit. Now, to experimentally determine the voltage across a parallel component, all you would do is just take and put a voltmeter. This diagram on pictorial level shows the 3 resistors and the voltage source at 12 volts, and notice that 4 voltmeters all read 12 volts. On the right-hand side, we have a schematic, and again, V sub S would be the voltage reading of each one of those meters. Again, the same voltage is across every component in a parallel circuit. What about the total resistance of 2 parallel resistors? Well, turns out the math is the simplest to do this. So if I have the case of 2 parallel resistors, the equations to determine the total resistance reduces to this equation. Our total is you multiply 2 resistors together and divide it by their sum. Okay? This will always give the result in a value less than this. This will always result in a value less than the smallest resistor value. This should make sense. Resistance is the opposition to the flow of current. 2 branches give more opportunity for current flow and thus less resistance. So here's some examples. This example 6.8 shows a circuit, figure 623, a voltage source, R1 of 680 ohms and R2 of 330 ohms. So down below, using that equation 6.3, R total is R1 times R2, or 680 times 330, and that multiplies out to 224,400 with ohms squared. Then to the denominator is R1 plus R2, 680 ohms plus 330 ohms, which adds up to 1010 ohms. And we do the math there, and we get 220, whoops, I don't like that. Should be well, no, it's a 1010 divided into 224,400. So that works out to be 222 ohms. The ohms down below the denominator cancels out one of the ohms in the numerator there. So again, what have we used? R total is R1 times R2 over R1 plus R2. Now, what about equal value resistors in parallel? This is the easiest. If one has several equal value resistors in parallel, the total resistance is given by R total is R divided by N, where N is the total number of resistors. And we'll have some examples of that. Notation for parallel resistors. The following notation is shorthand for parallel resistors. And I don't think on a keyboard there is this symbol, which is the parallel. This shows the notation indicates 5 resistors in parallel with each other. Those are resistors R1, R2, R3, R4, and R5. So let's take a look at Ohm's law in parallel circuits. Here is an example, figure 627. I've got a 100-volt battery. I've got R1 is 100K and R2 is 56K. Now, notice the 56 is not, down on the right-hand side of that line that's going downward. Instead, it's up above. Doesn't make any difference. Just think of rubber banding. I could take that R2 and pull it down to be in that other wire on the far right of that diagram. So since each resistor has the same voltage across it, one may determine the individual currents and add them, or determine R total and then determine I total. So in that example, they do it here. The individual resistance, the 56K and the 100K ohm resistor, works out to be 35.9 K ohms. The total current of the 100 volts divided by the 35.9 K ohms is 2.79 milliamps. Now, how could I do the current through either one of those resistors? Well, I just use the voltage divided by the resistance. So if R1 would be 100 volts divided by 100K, which would be 1 milliamp. Now, I know the total current is 2.79 milliamps, so what would happen is I would have 1.79 milliamps, the other amount of current, going through R2. And of course, if I divided 100 volts by 56 K ohms, I'd get 1.79 milliamps. So current dividers is the title of this slide. The total current in a parallel circuit divides among the branches into currents with values inversely proportional to the resistance values. So in a series circuits, if I add more resistance, there'd be more voltage drop. Here, it turns out the lower the resistance, the more the current. So this shows a diagram with a source. It's got 3 meters there. The total current's 110 milliamps. The current through I1, which is a 100 ohm resistor, is 100 milliamps. The current through I2, which is a 1,000 ohm resistor, is 10 milliamps. So it turns out that the current totals up to 110, the 100 plus the 10 total up to the total current of 110 ohms. I mean, we could figure out the voltage of the battery, but let's not do that right now. So if I have a current divider equation for 2 branches, it'll look like this. If there's only 2 branches, one can use the following equations to determine the branch currents. So I1 is equal to R2 divided by R1 plus R2 times I total. Notice in the numerator, it's the opposite resistor that you use. I2 is equal to R1 divided by R1 plus R2 times I total. So you use the opposite resistor to find out what the current is through the branches. Now, this is not nice stuff to do. It turns out you can have very complicated circuits, and there's a lot of calculation. Towards the end of this presentation, I'll talk about, say, Tinkercad or other circuit simulation software packages that do this stuff for you. So what about the power in parallel circuits? Well, again, total power in a parallel circuit is the sum of the individual powers. So the same equation we had before. If I had 3 parallel resistors, I would take power in power resistor number 1, power in resistor number 2, and power in resistor number 3, add them up to get my total power. And I'd use the power equations that I spewed out before to figure out what the power is per resistor. Now here's an example of parallel circuit applications. This is a simplified diagram of the exterior light system of an automobile. The automobile has a nominal 12-volt battery over on the left-hand side. And it turns out you see a couple switches here. The light switch, if I put that on, I'll apply 12 volts to what? The headlights, if I have the headlights on, and the parking lights, if I have them on, and the tail lights also. So those are kind of the running lights for the car. The brake lights, you see this momentary, it's a normally off, but a momentary on push button switch. And that's what happens when you step on the brake pedal of your car. You actually activate that switch and the brake lights on the back of the car turn on. If I put the transmission in reverse, what happens is it automatically closes that switch for the reverse backup lights and they will go on. So that's a parallel application, the same voltage applied to what? The headlights, parking lights, tail lights, brake lights, and backup lights. So parallel circuits are a way of distributing energy. Another example, this is a house example. I have 110 nominal volts. That symbol up there is a circuit breaker. Notice I have 2 lights attached, then I have 3 outlets. So that's an example of parallel circuits in residential wiring. So parallel circuits are used when we want to distribute power to many components, as would be the case in households or the automobile example shown previously. Okay, so we kind of switch gears a little bit here to talk about analog meters, which are basically obsolete. I asked you to look at the material and sun gauge, but again, it turns out most of the meters we use today are digital. This shows 3 meters here with these are analog meters, so notice they have a needle and a scale, and this shows 0.5 milliamps going through the analog meter, which is a 1 amp 50 ohm meter movement, and it goes up to halfway. And they work by principle of generating a magnetic field that moves the needle. 1 milliamp in the middle one, part B, goes full scale deflection. It'll go up to the full scale or 1, and greater than 1 milliamp will peg the meter and possibly destroy it on the far right-hand example. Another reason why we shouldn't really worry too much about analog meters at this point in time, when most of them, we can get very inexpensive digital meters. So these meters all work on the principle that a current will generate a magnetic field that will cause the meter movement to turn. In the case of these meters, 1 milliamp will cause a full-scale deflection, which is abbreviated FSD. So that brings us to combination circuits. Now, there's very few slides for this. You might say, well, I need more, but again, I don't want to bog you down with all kinds of calculations. As I said before, circuit simulation software is available that can solve these circuits. What you want to be able to do is to be able to ascertain what components are in parallel and what are in series. So in figure 7.1 here, it shows A, B, and C, and A shows terminals A and C and node B, and it's got resistor R1, R2, and R3. And the question is, what's in parallel and what's in series? Well, in the middle, part B, it shows these things shaded, and R1 is shaded, and then R2 and R3 together are shaded. And as it says, R1 is in series with a parallel combination of R2 and R3. So what would happen here? As shown here, the resistors in parallel, R2 to R3, are in series with resistor R1, and part C shows the flow of current. There's a total current coming out of the plus terminal, or node A. It goes through R1. There'll be a voltage drop across R1. Then at node B, the current splits up. I2 goes through R2. I3 goes through R3. Then at the bottom there, I2 and I3 would take and add together to form I total. So I total is equal to I2 plus I3. A more complex example, this shows, again, now 4 resistors. In part A, I've got R1, R2, R3, and R4, the red one that's been added. So what happens? R1 and R4 are in series with R2 and R3, which are in parallel when we look at them in the shaded view on the right. So in this case, R4 and R1 are in series with a parallel combination of R2 and R3. Another complex example is this one. Now we have 5 resistors. We've added an R5 to this one. And what do we have? Well, now we have R4 and R1 are in series. The other gray grouping to the right now, R2 and R5 are in series. And that series combination are in parallel with R3. So again, in this case, R4 and R1 are in series with a parallel combination. The parallel combination consists of the series grouping of R2 and R5 in parallel with R3. And this would start to be bothersome to take and calculate because there'd be a lot of calculations to figure out what's going on. So this says identify the series parallel relationship in figure 7.7. Again, you might take a look at that and say, okay, well, gee, I don't know what that is. They've redrawn it. You can always rubber band these things, it's a term. And the diagram on figure 7.8 is the same as figure 7.7. R1 is in series with 2 parallel combinations, R2 and R3, and R4 and R5. And again, you can always rubber band these things. And there's a, down very bottom of this example, 7.2, which shows how we might write this. R1 plus R2 in parallel with R3 plus R4 in parallel with R5. How to solve this, again, is another issue. Describe the series parallel combination between terminals A and D in figure 7.9 is example 7.3. So again, the solution there says there are 2 parallel paths. And it writes how this is all set up is that you got R1, resistor R1, plus the parallel combination of R5 and R6. Oh, excuse me. The parallel combination of R6 in parallel with, and you have to look at the, parentheses here. And I don't know if they have enough. It doesn't look like they have enough. R5 plus R4 in parallel with the combination of R2 plus R3. Well, again, you might want to take a look at that one a little bit longer. So how do we calculate the total current and branch currents? We first determine R total and then use Ohm's law to determine I total. Once I total has been determined, use the current divider equation to determine branch currents in parallel sections of a series parallel circuit. So here's an example. This one has 3 resistors. And the first thing it does is calculate an R total, which is 2.32 k ohms. Next thing it does is calculate an I total, 9.48 milliamps. Next thing it does is calculate I sub 2. And then it does I3 by taking and subtracting I2 from I total. And you can follow that example. Another way you could do this is you see a 22-volt source. You could find the total resistance, calculate the total current, then figure out what the voltage drop was across R1. Subtract that from the 22 volts, and that's the voltage across R2 and R3. And use Ohm's law. So, our summary here, circuit simulation software. You might feel overwhelmed by the number of concepts presented and the number of equations needed when talking about series and parallel circuits or even more complex series parallel circuits. Well, today there are several popular free circuit simulation software programs that can be used to analyze circuits. There's Circuit Maker, LT Spice, Tinkercad, and so forth, as well as some that are relatively inexpensive. Multisim, Tina, and so forth. These programs make solving circuits much easier. And stay tuned for a video about how to use Tinkercad. So that's it for this guy.